So this video lecturing thing is a little bit new for us at MST, so we're trying out a little bit of different format. So I'm going to try out a new format now and try to show you the slides this way and explain things. We've just seen SMA as a material and also a demonstration of the material. What I'm going to show now is some examples of SMA and how to use it in microsystems. So the first thing that we noticed is that SMA, to be able to use it as an actuator, actually it has to be deformed in the cold state. For completeness, I should say there's something called the one-way SMA effect and the two-way SMA effect. I'm only focusing on the one-way SMA effect because the two-way SMA effect, which actually has two stable states, that is an effect that loses its properties rather fast, and I don't know if it's very useful in microsystems, but you should know it exists. You can read a little bit more in Wikipedia on that, but I'm going to focus on the one-way SMA effect, the one that I've explained. So here we will cool the material in the cold martensitic state. We'll need to have an external force to deform it, otherwise nothing's going to happen by just temperature changing it, as I demonstrated with a little paper clip. So how are we going to do that? That means that in the cold state we should have some kind of a spring force or mechanical load deforming the SMA material, and then when we heat up the material it has to recover its shape and in that way perform work. And here we see an example of how that is done. We see it by an example of a microvalve. And a microvalve, basically a microvalve is a structure where it's a gas, in this case a gas microvalve, that controls the airflow. The air comes into the bottom orifice and goes out of the top orifice, and in the open state of course the air can flow, and in the closed state this boss structure is pressed down, and then the structure, there's no flow possible. So this is an open closed microvalve system. And how does this work? Well, this microvalve system consists of the boss is suspended by a shape memory alloy sheet, and here you can see it in the hot state, in the memory state, and here it's in the cold state. So in the hot state you see it's flat and the structure is open. In the cold state, however, there is you can see that at any moment there's also a silicon spring system here. So this is actually a spiral spring structure that is actually at any moment presses down on the boss. So in the cold state, when the SMA is easily deformable, the spring system basically presses down the boss and closes the valve. In the hot state, the shape recovery will be stronger than the spring force, and the valve will be pushed open. So at any time there is a balance between two forces here, and it's the force of the spring system, the silicon spring system, pressing down the boss, and of the SMA sheet that actually pushes up, that at any time pushes up the boss. But in the martensitic state, the material is too deformable, or you could say the stiffness is too low to counteract the silicon spring, and in the hot state it is stronger than the spring. So cold state, the spring is stronger than the SMA, hot state, the SMA is stronger than the spring system. And that shows like really how we need to build in a spring system to be able to get SMA to work. Another example you can see here is a micro gripper. There are two silicon pieces. They are etched by deep reactive ion etching, as you obviously can see. You should understand that now. Why does this deep reactive ion etching? You should be able to recognize it from the shape. And on both the top side and the bottom side, there's deposited a thin SMA layer. The position of this thin SMA layer causes a stress. So when cooling, so you deposit at a hot temperature, and cooling, you get actually bimorph between the SMA and the silicon, and the whole structure will be stressed and be pulled open. So they're bonded here, but not on this part. So the whole structure, the stress will deform, like a thermal bimorph, deform the structures. But heating it up, the system will recover and will become totally flat, and then you will have a gripping effect between these two claws here. On the bottom, you see yet another example. This is a microvalve that's been developed by my team at KTH here. And it consists basically of an airflow coming in on the bottom here and wanting to go out here to the front. But there's the gate structure here that blocks the flow. That's an in-plane flow that you have here. So when the gate is down, it's blocked. When the gate is pushed open by the air pressure, the air can go through. So in the cold state, the SMA is deformable, and the air pressure here will push open the valve. such that the gate opens. You can see that actually here the gate is open, the air can flow out. And in the closed state, when the SMA is hot, the gate is closed and the airflow cannot go out. SMA is often used in medical systems, not only microsystems, but also in medical microsystems, but in medical system in general. And probably one of the most common applications is that of stents for coronary angioplasty. So what is coronary angioplasty? Well, this is if you have a vein or an artery that is clogged by plaque, then of course you get there's a problem. For one, the heart will have to work too hard to get the blood through, so it's not good for the heart. Secondly, there's a risk that this clots like free up and cause a stroke. So you don't want that. So people that have that, one very common operation is a balloon dilatation operation, in which via catheter you bring in a balloon and you blow up the balloon, and then the whole you basically widen the structure, and when the balloon deflates, you have basically pressed open the artery. Now, where is the SMA coming in? Well, there's around the balloon there often is a SMA net structure, like a cylindrical wire structure, and in the cold state, it's compressed around the catheter, so it's easily to bring in the place. And when you heat it up, or in this case, yeah, you use the balloon to heat it up and to expand it, then it recovers its memory state, which holds then the system open and prevents it from collapsing again. So SMA is very often used for this kind of applications. Another example of using SMA in microsystems is that of endoscopes, or this is a microendoscope, so also for looking either in the intestines or in the throat or in the veins. And then of course this is like a wire-like structure, you can see, but you want to be able to control the tip to see, to steer it in one direction or another. And then what they do is they integrate little shape memory alloy actuators at the tip, so the tip can be freely rotated using the SMA actuators, and you can actually steer it freely as you want remotely, and it's controlled via little heaters.